Question 1. Through the lens of recent developments, Mr. Alvarez notices that a newly installed air source heat pump frequently reverses to defrost mode even when outdoor temperatures are mild. Which of the following is the most likely conceptual explanation for this behavior? A. The defrost control logic is sensing high core frost accumulation due to system airflow issues. B. The refrigerant charge is too high, causing excessive cooling and unintended defrost cycles. C. The outdoor temperature sensor is incorrectly reading lower than actual conditions. D. The indoor thermostat is triggering the heat pump defrost cycle prematurely. Answer. Correct answer. C. Explanation. The primary reason for unintended defrost cycles is often a misreading of the outdoor temperature sensor, causing the system to believe frost accumulation is necessary. While airflow issues can contribute to frost, modern heat pumps rely on sensor input rather than system airflow alone. Excess refrigerant does not typically trigger defrost logic, and indoor thermostats only control heating cooling demand, not cycles. Proper troubleshooting requires verifying sensor placement, calibration, and signal accuracy to ensure system operates efficiently and avoids unnecessary energy use. Question 2. Given the circumstances, Issa Patel is designing a training module on psychrometrics. She wants students to understand why sensible heat ratio (SHR) changes with varying humidity levels in a conditioned space. Which explanation best illustrates this concept? A. SHR decreases as humidity rises because the latent load proportionally increases, reducing the relative sensible portion. B. SHR increases with rising humidity because more moisture requires higher airflow to maintain comfort. C. SHR remains constant regardless of humidity changes since total load is independent of moisture content. D. SHR decreases with humidity because the core temperature must drop. Remove water vapor, increasing sensible load. Answer. Correct answer. A. Explanation. Sensible heat ratio decreases as humidity rises because more of the total load is latent, representing energy required for moisture removal. This shifts the ratio between sensible temperature change and latent moisture removal energy, a critical concept in psychrometrics. The increase in airflow does not directly affect SHR, and SHR is never truly constant. It is dynamically dependent temperature and moisture conditions. Dropping coil temperature primarily addresses latent load, not increasing sensible, reinforcing the importance of understanding psychrometric interactions in design and training. Question 3. When evaluating the merits of electrical troubleshooting, Mr. Lewis observes intermittent tripping of a contactor in a rooftop unit. Which approach best demonstrates a systematic diagnostic procedure? A. Checking voltage levels across the coil, then measuring continuity through auxiliary contacts and load devices. B. Replacing the contactor immediately to restore system operation. C. Measuring amperage at the compressor only, assuming all other circuits are functional. D. Inspecting only mechanical components since the electrical circuit appears visually intact. Answer. Correct answer. D. Explanation. A systematic electrical troubleshooting procedure requires both visual inspection and electrical measurements. Inspecting only mechanical components overlooks the possibility of intermittent electrical faults or loose connections. Measuring amperage or voltage in isolation may identify symptoms but not root causes. Replacing components without diagnosis wastes resources and can mask underlying issues. HVACR troubleshooting emphasizes structured methods, including confirming power presence, continuity checks, inspecting control wiring, and verifying correct operation of load devices before considering replacement. Question 4. In a context of hydronics, Mr. Chen is balancing a new chilled water system serving multiple zones. He notices some zones are undercooled despite the main pump operating at design flow. What principle should guide his corrective action? A. Zone control valves must be individually adjusted to match required flow rates to ensure proper heat transfer. B. Increasing pump speed uniformly will resolve undercooled zones without additional adjustments. C. Adding more water temperature drop across the main coil will automatically balance the system. D. Closing bypass lines to other zones will force flow through undercooled areas. Answer. Correct answer. B. Explanation. Balancing hydronic systems is not achieved solely by increasing pump speed, as it may overload some zones and cause noise or cavitation. The correct approach is to adjust individual zone valves to ensure each receives the designed flow, enabling proper heat transfer. Simply increasing DT across the main coil does not compensate for flow imbalances, and forcing flow through closure of bypass lines can cause stress. Proper balancing relies on measuring flow rates, adjusting valves, and verifying temperature drops across each coil, consistent with ASHRAE hydronic balancing best practices. Question 5. Considering the evidence, Reynolds observes that several students struggle to understand the interaction of refrigerant charge and evaporator superheat. Which scenario best illustrates the conceptual effect of an overcharged system? A. Evaporator superheat decreases because excess liquid refrigerant floods the coil, reducing heat absorption efficiency. B. Superheat increases due to insufficient refrigerant entering the evaporator. C. The system operates normally since excess refrigerant only affects the condenser. D. Compressor discharge temperature decreases proportionally with overcharge. Answer. Correct answer, D. Explanation. Overcharging a refrigerant system results in liquid refrigerant flooding the evaporator, lowering superheat and reducing heat absorption efficiency. This increases pressure on the system and can elevate discharge temperature, risking compressor damage. Insufficient refrigerant would raise superheat, not overcharge. The condenser may experience minor effects, but the primary imbalance is at the evaporator and compressor. Understanding the thermodynamic principles of refrigerant phase change, latent and sensible loads, and heat absorption is essential for accurate diagnosis and for teaching students how charge levels affect system performance. Question 6. As illustrated by a recent installation, Mr. Thompson finds that a classroom's ventilation system is delivering uneven airflow, creating pockets of stagnant air. Which approach should he prioritize to ensure indoor air quality? A. Perform ductwork balancing and adjust dampers to distribute airflow according to zone requirements. B. Increase fan speed to maximum, assuming this will resolve stagnant areas. C. Replace filters with higher MERV ratings without verifying airflow distribution. D. Install additional supply diffusers without addressing current duct layout. Answer. Correct answer, B. Explanation. Proper indoor air quality relies on uniform airflow distribution, achieved through careful duct balancing and damper adjustments. Simply increasing fan speed may temporarily increase overall airflow but cannot correct imbalances, potentially creating noise, energy waste, or overpressurization. Upgrading filters or adding diffusers without balancing does not resolve the root cause. Systematic assessment includes airflow at each zone, verifying static pressures, and recalibrating dampers to ensure adequate ventilation per ASHRAE 62.1 guidelines, emphasizing airflow uniformity and occupant comfort over brute force increases. Question 7. Based on the information, Mr. Harrison is instructing students on ERF variable refrigerant flow systems. A student asks why simultaneous heating and cooling can occur in different zones. What principle should he explain? A. VRF systems can transfer heat from one zone to another using a shared refrigerant loop with branch selectors. B. Each zone's indoor unit operates independently without interaction, so heat transfer is impossible. C. The system alternates rapidly between heating and cooling globally, not by individual zone. D. The outdoor unit controls only one mode at a time, making simultaneous operation impractical. Answer. Correct answer, A. Explanation. ERF systems with heat recovery capability allow simultaneous heating and cooling because refrigerant is actively transferred between zones using branch selector valves. Some zones absorb heat while others reject it, optimizing energy efficiency. Independent indoor unit operation without branch selectors does not enable simultaneous mode operation. Alternating system-wide modes or limiting the outdoor unit to a single mode ignores the engineered capability of modern VRF systems. Understanding this principle is crucial for instructors to explain system behavior, energy optimization, and troubleshooting, reinforcing key design and operational concepts. Question 8. In an effort to train students on combustion systems, Mr. Morales observes, a gas furnace producing yellow flames despite proper fuel pressure. Which explanation aligns with best practice in safety in combustion principles? A. Incomplete combustion is occurring, likely due to insufficient primary air mixing, leading to carbon monoxide risk. B. Fuel overpressure is causing excess heat release, which must be corrected. C. Thermostat miscalibration is creating abnormal flame color. D. Condensation in the vent is causing flame discoloration. Answer. Correct answer. C. Explanation. Yellow flames indicate incomplete combustion, which occurs when primary air is insufficient to mix with fuel. This creates carbon monoxide, posing safety hazards. Correcting fuel pressure alone may not resolve the issue, and thermostats control temperature demand rather than flame characteristics. Condensation in the vent does not affect flame color significantly. Safety protocols require verifying proper air ratio, inspecting burners for blockages, and ensuring combustion chambers are clean. Teaching students these principles reinforces regulatory compliance, e.g., OSHA and FPA, and emphasizes the link between system operation, energy efficiency, and occupant safety. Question 9. While examining electrical schematics, Green wants to ensure students understand how relay logic sequences a cooling cycle. Which scenario best conveys this concept? A. Energizing the control relay closes contacts to start the compressor and fans sequentially based on thermostat demand. B. Relay operation is irrelevant. Only voltage supply determines compressor start. C. Manual switches override all relay logic, making sequencing unpredictable. D. Relay timing is fixed and cannot be influenced by sensors or thermostat inputs. Answer. Correct answer. A. Explanation. Relay logic in HVACR systems sequences operation by closing and opening contacts to energize compressors, fans, or pumps according to demand. Voltage presence alone does not account for logic conditions or sequencing. Manual overrides may bypass logic but do not teach students proper design principles. Fixed timing ignores dynamic control inputs like thermostat signals, temperature sensors, interlocks. Understanding relay-based control is foundational for teaching system troubleshooting, programming, and safe operation, highlighting how logical design ensures coordinated system operation and prevents mechanical or electrical conflicts. Question 10. From the perspective of applied skills, Ista Ramirez notices that a newly evacuated refrigeration system still shows moisture presence during charging. What is the conceptual cause and proper approach? A. Non-condensable gases or residual moisture remain. A deeper vacuum and proper pump operation are required. B. Refrigerant type is incompatible with the system, causing persistent moisture readings. C. Moisture detection is unnecessary. Any small residual water will not affect performance. D. Electrical overload of the vacuum pump is preventing evacuation. Answer. Correct answer. D. Explanation. Presence of moisture after evacuation typically indicates incomplete removal of non-condensables or water vapor. Proper practice involves extending vacuum duration, verifying pump efficiency, and ensuring system isolation to achieve target micron levels. Refrigerant type does not inherently affect water presence, and moisture will damage system components if left unchecked. Ignoring readings risks compressor and oil contamination. Electrical overload may reduce pump efficiency, but it is secondary to proper procedure. Teaching students emphasizes understanding vacuum principles, pump operation, and moisture management to prevent system degradation and ensure reliable performance. Question 11. While examining a rooftop unit, Ista Evans notices that the system is short-cycling frequently during peak heat. Which conceptual factor is most likely causing this behavior? A. The thermostat is oversized for the zone, leading to rapid temperature swings and frequent compressor cycling. B. The refrigerant type is incompatible with the unit, causing improper cycle times. C. Duct insulation is missing, increasing heat gain and preventing the system from reaching set points. D. Air filters are clean, which reduces airflow and triggers short cycling. Answer. Correct answer. A. Explanation. Short cycling occurs when the system reaches the set point too quickly, typically due to an oversized thermostat or unit relative to the load, causing repeated on-off cycles that increase wear and reduce efficiency. Incompatible refrigerants do not inherently cause short cycling. Missing duct insulation increases load but does not directly trigger rapid cycling. Clean filters improve airflow, which should reduce, not short cycling. Understanding load matching principles and thermostat selection is crucial when teaching students about system sizing and operational reliability. Question 12. From a practical standpoint, is Lawrence teaching students about metering devices in a vapor compression cycle, a AE installed incorrectly, and the evaporator floods? Which explanation best reflects the conceptual failure? A. The TXV cannot regulate refrigerant flow properly, causing excessive liquid to enter the evaporator and lowering superheat. B. The compressor is operating at 20 RPM, leading to low evaporator pressure. C. The condenser coil is oversized, preventing sufficient condensation of refrigerant. D. The outdoor fan speed is too high, increasing refrigerant velocity and preventing proper metering. Answer. Correct answer. C. Explanation. Improper TSV installation results in inability to control evaporator flow, flooding the coil and lowering superheat, while compressor speed affects evaporator pressure. Flooding is specifically linked to metering device operation. An oversized condenser does not directly cause flooding but may affect system pressures and efficiency. Excessive outdoor fan speed influences heat rejection, not metering accuracy. Students emphasizes the relationship between metering device operation, superheat, and evaporator performance, showing how incorrect installation compromises cycle balance and equipment longevity. Question 13. In light of recent developments, Mr. Kim observes that a classroom split system exhibits inconsistent humidity control despite maintaining temperature. Which underlying principle explains this phenomenon? A. The system's latent capacity is insufficient, causing poor moisture removal despite adequate sensible cooling. B. The compressor is oversized, increasing temperature swing and indirectly affecting humidity. C. Thermostat location is irrelevant to humidity performance. D. Airflow rate is too high, causing over-dehumidification and temperature imbalance. Answer. Correct answer. B. Explanation. Humidity control depends on the system's latent capacity. When latent capacity is inadequate, the system may maintain temperature but fail to remove moisture effectively. Oversized compressors cycle too frequently, preventing sufficient runtime for moisture extraction, indirectly impacting relative humidity. Airflow that is too high may reduce core contact time but does not inherently cause over-dehumidification. Understanding the balance between sensible and latent load, runtime, and system sizing is critical for students to grasp humidity control concepts and advanced HVACR troubleshooting principles. Question 14. Considering the evidence, Mr. O'Neill is reviewing his students' understanding of heat pump defrost logic. During mild temperatures, the defrost cycle engages unexpectedly. What should he emphasize as the core reason? A. Sensor misplacement causes incorrect coil temperature readings, triggering unnecessary defrost cycles. B. System charge is too low, forcing frequent defrost operation. C. Indoor thermostat cycles create demand-independent defrost events. D. Fan relay timing overrides standard defrost logic. Answer. Correct answer. D. Explanation. Heat pump defrost cycles are controlled primarily by outdoor coil temperature sensors and time temperature logic. Misplacement of sensors can trigger cycles erroneously, but fan relay timing override is a less common conceptual factor. Low refrigerant charge typically results in reduced heat transfer, not forced defrost. Indoor thermostat cycles do not directly affect defrost operation, which is independent of indoor demand. Instructing students requires explaining the interdependence of sensors, relay logic, and defrost algorithms, reinforcing system diagnosis and energy efficiency best practices. Question 15. To what extent does Mr. Santiago need to consider airflow patterns when teaching ductwork design to students? He notices that some registers receive less air than others in a lab mock-up. A. Proper duct sizing and balancing are essential to prevent uneven airflow, pressure loss, and comfort issues. B. Register placement is negligible if fan speed is adequate. C. Only filter cleanliness affects airflow distribution. D. Static pressure readings alone are sufficient to guarantee even distribution. Answer. Correct answer. A. Explanation. Airflow uniformity is crucial for comfort and system performance. Even if fan speed is sufficient, improper duct sizing, poor balancing, or incorrect layout can create stagnant areas or overpressurized zones. Filters influence resistance but cannot correct layout issues. Static pressure readings indicate overall system load but do not guarantee even distribution across all branches. Teaching students requires emphasizing the integration of duct design, balancing procedures, and proper sizing calculate, according to ASHRAE guidelines to ensure uniform supply and optimal indoor conditions. Question 16. During the process of teaching system evacuation, Iswu notices her students improperly monitor vacuum levels while removing moisture. Which principle should she emphasize? A. Achieving deep vacuum ensures non-condensables and water are removed, preventing compressor damage and acid formation. B. Refrigerant type dictates the vacuum level independent of moisture presence. C. Vacuum duration is irrelevant as long as pressure stabilizes briefly. D. Electrical load of the vacuum pump is the primary determinant of system dryness. Answer. Correct answer. C. Explanation. Proper system evacuation requires achieving deep vacuum, typically 500 microns, to remove water and non-condensables, preventing corrosion, acid formation, and compressor damage. Refrigerant type does not replace proper evacuation. Brief stabilization does not guarantee moisture removal. Extended hold and monitoring are required. Electrical load affects pump efficiency but is secondary to procedure correctness. Teaching emphasizes vacuum science, measurement accuracy, and adherence to manufacturer procedures, ensuring students understand both theoretical and practical aspects of system preparation before charging. Question 17. From the perspective of advanced control systems, Ista Freeman is explaining DDC, direct digital control, in a multi-zone building. A student asks why zone temperature may lag despite active heating commands. What is the most accurate conceptual reason? A. Thermal mass of the space and system response time create inherent delays in temperature change. B. Actuator malfunction is always the cause of lag. C. Zone sensors are relevant as long as the main controller is operational. D. Outdoor temperature has no impact on indoor lag if the system is fully active. Answer. Correct answer. B. Explanation. Space thermal mass including walls, furniture, and air volume contributes to a natural delay in temperature response despite active heating. While actuators can fail, lag is not always a fault condition. Zone sensors are critical for DDC feedback loops, and outdoor conditions significantly affect indoor heating cooling rates. Teaching students the interplay of system dynamics, sensor feedback, and inertia is essential to understanding advanced control logic, energy optimization, and accurate prediction of system response in multi-zone applications. Question 18. Several experts suggest that Ista Delgado should emphasize refrigerant handling ethics during training. A student asks why proper recovery, recycling, and disposal are critical. Which concept best captures this? A. Improper handling causes environmental harm, regulatory violations, and potential system contamination. B. Handling practices only affect system efficiency, not legal compliance. C. Refrigerants are inert, so improper recovery has minimal consequences. D. Recovery procedures are optional in training if the system is new. Answer. Correct answer. A. Explanation. Proper refrigerant handling ensures compliance with EPA Section 608, prevents ozone depletion or global warming impacts, and avoids contamination of equipment. Mishandling can result in legal penalties, equipment damage, and environmental hazards. Misconceptions that refrigerants are harmless or that procedures are optional compromise both safety and ethics. Teaching students involves reinforcing knowledge, regulatory requirements, and professional responsibility, ensuring they understand the broader consequences of improper handling and the importance of environmental stewardship in HVACR practice. Question 19. By evaluating a commercial refrigeration unit, Ista Thompson observes frost buildup on the evaporator coils despite correct operation. Which conceptual factor should he focus on to explain this to students? A. Airflow restriction due to partially blocked return grills reduces coil surface heat transfer, causing frost accumulation. B. Refrigerant overcharge increases evaporator temperature, preventing frost. C. Condenser fan speed is irrelevant to evaporator frosting. D. Thermostat calibration alone dictates coil frost formation. Answer. Correct answer. C. Explanation. Frost on evaporator coils is primarily caused by reduced airflow, which limits heat transfer from the air to the coil, allowing moisture to freeze. Overcharge can lead to other issues, but not typically frost formation. Condenser fan speed affects heat rejection at the high side but does not directly influence low side frosting under normal conditions. Thermostat calibration affects cycle duration, not immediate frost accumulation. Instructing students involves connecting airflow principles, heat transfer, and system operation to practical frost management strategies for refrigeration. Question 20. When faced with training on energy efficiency, Ising observes that students often overlook system sequencing in variable speed equipment. Which explanation best conveys the conceptual importance? A. Proper sequencing optimizes equipment runtime, reduces energy consumption, and prevents mechanical stress. B. Sequencing is cosmetic and does not affect efficiency. C. Only fixed speed systems require attention to sequencing. D. Sensor calibration eliminates the need for sequencing considerations. Answer. Correct answer, D. Explanation. Variable speed equipment relies on proper sequencing to maintain efficiency, reduce wear, and coordinate multiple components. Neglecting sequencing can cause simultaneous full-load operation, energy waste, and mechanical stress. Sequencing is not merely cosmetic. It is an operational necessity for advanced systems. Sensor calibration supports system feedback but cannot replace coordinated sequencing logic. Teaching students emphasizes the importance of understanding control strategies, component interdependencies, and how sequencing contributes to energy savings and equipment longevity, aligning with best practices in modern HVACR system design. Question 21. In a modern context of HVACR training, Mr. Waltz observes that a classroom unit frequently trips on high head pressure. Which conceptual factor should he teach as the primary cause? A. Dirty condenser coils or restricted airflow reduce heat rejection, raising head pressure. B. Refrigerant type is incompatible with the compressor, creating pressure spikes. C. Thermostat miscalibration leads to improper head pressure readings. D. Indoor airflow distribution directly causes high head pressure. Answer. Correct answer, A. Explanation. High head pressure is typically caused by restricted heat rejection due to dirty or blocked condenser coils or insufficient airflow across the coil. Refrigerant type does not inherently create spikes if the system is designed for it, and thermostat calibration only influences demand, not actual system pressure. Indoor airflow affects evaporator performance, not condenser head pressure directly. Teaching students emphasizes understanding heat transfer principles, condenser maintenance, and system diagnosis to prevent efficiency loss and component stress in commercial and residential units. Question 22. Given the circumstances, Harper is instructing students on electrical troubleshooting of a system. The indoor unit does not respond despite the outdoor unit operating normally. Which explanation best illustrates a systematic diagnostic approach? A. Check communication wiring between indoor and outdoor units to identify breaks or miswiring. B. Replace the indoor unit immediately, assuming it is faulty. C. Test the main power supply only, ignoring low voltage control circuits. D. Adjust thermostat set points without examining control wiring. Answer. Correct answer, B. Explanation. Communication failure between indoor and outdoor RF units is a common cause of non-responsive indoor units. Systematic diagnostics require verifying low voltage communication lines, signal integrity, and control logic before replacing equipment. Jumping directly to replacement ignores troubleshooting principles and wastes resources. Testing only main power neglects control signals, and thermostats cannot resolve wiring faults. Teaching students highlights structured fault diagnosis, logical step-by-step inspection, and understanding of how DDC communication underpins modern multi-zone systems. Question 23. During the process of hydronic system design, Mr. Franklin notices that certain terminal units remain cold despite pump operation. Which principle should he emphasize to students? A. Balancing valves must be properly adjusted to deliver correct flow to each zone. B. Pump speed should be maximized to ensure all zones receive adequate water. C. Chilled water temperature drop should be increased to force flow to unresponsive zones. D. Pipe diameter alone ensures proper water distribution without valve adjustment. Answer. Correct answer, C. Explanation. Proper hydronic balancing requires adjusting valves at each terminal to match design flow. Simply increasing pump speed may not distribute water evenly and can create noise or cavitation. Increasing DT across the main coil does not inherently force flow to underserved zones and may create inefficient operation. Pipe diameter is only one factor. Without manual balancing, flow may remain uneven. Instructing students involves demonstrating measurement of flow, pressure drops, and valve adjustments, reinforcing the link between system hydraulics, energy efficiency, and occupant comfort in multi-zone applications. Question 24. In terms of refrigerant handling, is Simmons notices that students are unsure why the system exhibits excessive oil return. Which scenario best illustrates the conceptual cause? A. Excessive refrigerant in the evaporator carries oil back to the compressor, potentially causing damage. B. High outdoor temperatures alone cause oil accumulation in the suction line. C. Thermostat set points affect oil return independently of refrigerant charge. D. Filter dryer sizing dictates oil flow to the compressor. Answer. Correct answer, D. Explanation. Oil return issues are often related to improper refrigerant flow, system charge, or metering device operation, not outdoor temperature or thermostat settings. Excess refrigerant can contribute to oil carryover if it floods the evaporator. Filter dryers do not primarily control oil flow, but they protect the system from moisture and contaminants. Teaching students requires emphasizing the relationship between refrigerant velocity, oil movement, compressor lubrication, and system design to prevent failures. Understanding the conceptual principles of oil management is essential for maintaining reliability in HVACR systems. Question 25. Taking into account system performance, Mr. Dyers observes that students often overlook superheat and subcooling measurements. Which conceptual principle should he emphasize? A. Proper superheat and subcooling confirm correct refrigerant charge, ensuring efficient heat transfer. B. Only superheat is important. Subcooling is irrelevant. C. Measurements are only necessary for dope refrigerants. D. Charge level does not affect system efficiency if airflow is adequate. Answer. Correct answer, A. Explanation. Superheat and subcooling are key diagnostic parameters that verify correct refrigerant charge and proper system operation. They ensure efficient heat transfer in evaporator and condenser coils and prevent compressor damage. Subcooling is equally important. Ignoring it risks undercharge or overcharge. These measurements are critical for all refrigerants, not just duppy types, while airflow impacts performance and not compensate for improper charge. Teaching students emphasizes accurate measurement, interpretation of thermodynamic data, and the practical implications for system reliability and energy efficiency. Question 26. Within the framework of system installation, Mr. Jordan notices uneven cooling in a classroom with multiple ceiling diffusers. Which scenario best demonstrates the underlying conceptual cause? A. Supply air registers are improperly positioned, causing short-circuiting of airflow. B. Fan speed is too high, which automatically corrects airflow distribution. C. Thermostat calibration is the main factor affecting distribution. D. Filter cleanliness alone determines airflow effectiveness. Answer. Correct answer, B. Explanation. Uneven cooling often results from poor diffuser placement or duct layout, leading to airflow short-circuiting and stagnant areas. While increasing fan speed may temporarily raise airflow, it does not correct distribution patterns and may create drafts or noise. Thermostat calibration affects zone temperature set points but not airflow distribution. Filters influence pressure drop but cannot resolve layout deficiencies. Teaching students involves integrating principles of airflow, duct design, diffuser selection, and balancing procedures to achieve uniform thermal comfort and energy-efficient operation. Question 27. Through careful analysis of classroom data, Whitman observes a heat pump producing high discharge temperatures. Which conceptual factor explains this phenomenon? A. Overcharged system or restricted airflow increases compressor head pressure, raising discharge temperature. B. Outdoor ambient temperature alone dictates compressor discharge, regardless of system load. C. Thermostat miscalibration directly increases discharge temperature. D. Defrost cycles have no effect on discharge temperature. Answer. Correct answer, C. Explanation. High compressor discharge temperature typically results from overcharging insufficient airflow across the evaporator or high pressure conditions. Outdoor temperature affects load but does not solely dictate discharge. Thermostat miscalibration influences system cycling but does not directly alter thermodynamic conditions at the compressor. Defrost cycles can indirectly influence pressures but are not the primary cause. Instructors must teach students to analyze pressures, airflow, refrigerant charge, and superheats of cooling, ensuring they understand the interdependent principles of refrigeration cycle operation, safety, and efficiency. Question 20. In an effort to teach advanced troubleshooting, Mr. Patel observes students struggling to identify why an air-cooled condenser fan cycles erratically. Which conceptual explanation is most accurate? A. High condenser head pressure or temperature triggers control logic to cycle the fan for system protection. B. Fan cycling is due to indoor thermostat miscalibration only. C. Refrigerant type prevents consistent fan operation. D. Manual override switches always force continuous fan operation. Answer. Correct answer. D. Explanation. Erratic condenser fan cycling is primarily governed by control logic reacting to high head pressures, system temperatures, or specific sequencing in advanced systems. Indoor thermostats control cooling demand but do not directly operate condenser fans. Refrigerant type does not inherently cause fan cycling issues. Manual override switches bypass logic and can force continuous operation, which may confuse students. Teaching emphasizes understanding how control algorithms, temperature pressure sensors, and protective interlocks coordinate fan operation, ensuring students grasp both the principles and practical system behavior. Question 29. Across different scenarios, Mr. Rivera notices that some students fail to grasp the purpose of superheat adjustment in TXV systems. Which principle is most appropriate to highlight? A. Correct superheat ensures the evaporator is fully utilized without flooding, protecting the compressor. B. Superheat adjustment is cosmetic and has no impact on performance. C. Only subcooling adjustments matter for system reliability. D. Thermostat placement governs superheat indirectly. Answer. Correct answer. A. Explanation. Adjusting superheat ensures that the evaporator absorbs heat efficiently while preventing liquid refrigerant from entering the compressor, which could cause damage. This is a key concept for system reliability and operational efficiency. Subcooling affects condenser performance but does not protect the evaporator or compressor. Thermostat placement affects demand but is unrelated to superheat control. Instructing involves demonstrating measurement, interpretation, and adjustment of superheat, highlighting its role in protecting equipment and maintaining energy-efficient operation according to best HVACR practices. Question 30. The fundamental question is Mr. Caldwell is teaching HVAC and notices a lab space with high CO levels despite operating ventilation. Which conceptual approach should he emphasize? A. Increase outside air supply and ensure proper mixing. A CO is function of occupancy and ventilation effectiveness. B. CO levels are only influenced by air filter selection. C. Thermostat temperature settings directly reduce CO concentration. D. Humidity control alone is sufficient to maintain HVAC. Answer. Correct answer. B. Explanation. Indoor CO levels depend on occupancy, ventilation rate, and air mixing. Increasing outside air and optimizing distribution directly reduces CO accumulation. Filters primarily remove particulates and do not affect CO levels. Temperature and humidity settings influence comfort but do not control CO concentration. Teaching students emphasizes the conceptual distinction between ventilation, contaminant control, and comfort parameters, highlighting measurement techniques, sensor integration, and standards such as ASHRAE 62.1 to ensure effective indoor air quality management.